Hello everyone. Today we are going to talk about our solution for this year's Grand Challenge. My name is Zongshun Zhang, and my friend Ethan is also here. We will share with you our ideas and go through our solution. This is the outline of today. So we will go over the background and the motivation for our solution and the implementation architecture of our solution also. And we will talk about the result, which is basically the rank in the breeder system. At the end of today, we will also mention some future work and some discussion point at the end. First, we will go through the background. This year's grand challenge is to find a great and optimized algorithm for NILM monitoring system, which refers to non-intrusive load monitoring. The event model we used for pattern matching is basically from the paper that was cited from the question prompt. We have the reference at the end of this slide, so if any will go interested in it, you may go to the end of this video and you will see the reference. Because there are a lot of existing distributed stream processing engine there, so we basically take advantage of one of them, the Apache Flink, to help us to handle all the low-level implementation and some great feature. Say here, we take advantage of Apache Flink of its ability to handle parallelism management, and event time-driven management processing. And also its distributed communication method, and also its load balancing method. Other than the framework, we also take the idea of DBScan clustering algorithm to do the event detection, and also in terms of deployment, we take advantage of Docker Compose and Docker Container to actually deploy our solution. One thing I would like to emphasize is that inside Apache Flink, the parallelism management system is quite useful for our solution. They have implemented operator and task level parallelism. So you can see here the graph on the top. This is job graph that can be specified by the user. You can specify the operator and its transformation inside of each operator. And then the Apache Flink will try to compile and translate the job graph into an execution graph here. You can see here each of the instances of the operator has some number of parallelism. And also the communication channel between each of the operator would be handled by the Apache Flink.
So moving on, DB scan clustering is one of the most popular clustering algorithm out there. It's also the one that was used in a baseline and used in our solution architecture. And the reason why is because it's easy to use and modifiable, which allows it to be used in many situations. It requires two arguments, the minimum points, which is the minimum number of points required before DBScan will consider a set of points to be a cluster, and the epsilon, which is the radius. This is like the range in the picture. You can see that n is outside the radius, and because it's outside that radius, it is no longer considered part of the cluster that is the red cluster in the picture. And moving to the solution architecture, the first thing that we did was moving from Python to Java. Java is a compiled language. Unlike Python, which is an interpreted language, the advantage is that it's usually faster because there's a lower layer. And second is the use of Flink. And we use Flink because it has an extensive set of features that allows us to multi-thread and parallelize jobs within its operator. It also supports a lot of event time management and state management, which allows for the data streaming application to maintain like state. And essentially, all these utilities help create a very robust data streaming application.
And then we will go a little bit deeper inside the implementation of our solution. So here you can see that this is the graph for our query one. Each of the boxes here indicates a operator, and each of the operator can have multiple level of parallelism. And the arrow here indicates the direction of our data flow. So here you can see that in the query one, we have a dedicated operator to get batches of records, which includes voltage and current values. And then we will have a key by grouping, basically based on the first record ID in each batches to do load balancing. And then for each of the batch, if each batch of the record, we will convert that to power values. And here we will have some level of parallelism. And then we will try to order those power values that were generated in parallel in terms of the ordered records, power records. We will do clustering to do the event detection, basically to find the power value change inside of the data. In the end of the data flow, we would simply post the event detection result to the grid. You guys may already see that there are actually two bottlenecks here. The first one is for the merge and ordering step. The problem here is that there isn't a good or easy implementation to ordering everything with more than one thread. I mean, if we have several threads generating the power event power records, and then we always have to have one thread to get all the records together and do the ordering. And so this is something hard to mitigate. And on the other hand, in the real world implementation, the deployment, we will try to put this kind of operator in a single but high capacity node to try our best to mitigate this problem. Following that, on the second bottleneck here, we were using the basic implementation of DBScan algorithm, which means each time we get a batch of data, and then we simply do clustering on that batch from scratch. We also thought about other two ways to do this to do the clustering. The first thing is using parallelism. The idea is that we can basically do several clustering jobs at the same time, while using the parallelism to hide the time we actually doing the same job, right? Same job. But the problem with this kind of method is that we will pay more for the computation power. On the other hand, we also thought about reuse the previous clusters we already developed earlier, right? We don't do any redundancy work here, right? So it's cheap. But on the other hand, the operator to handling this kind of job will be very stable. So basically, these two directions was not quite work out. So in the end, the implementation was simply using the basic idea, get a batch and do clustering from scratch. Even though this is not cost effective, but somehow it's a balance between cost in terms of computation power and the state. We'll have a further discussion about these two things, about these two clustering methods later in the presentation. And then we also have the data flow for query 2. The difference between query 1 and query 2 is that in query 2, we will have out of order records. So here we will have these two operators to handle this problem. Here we try to, in the first operator, we try to extract the record ID for in terms of each record. On the contrary, that previously we were just using the first record ID of each batch, right? And then we will try to do load balancing at the level of each record. And then we have another operator to basically wait for the records to come and then accumulate based on the time, based on the ID, and then accumulate them to be some batches, and then go through the same procedure like before. We will transform the batch into power, and then ordering the batches and then to clustering and then post the results.
Moving towards the result, as seen from this table, our result is ranked 6 overall, but our total rank is actually 21 when you add up all the rank. And the first thing you notice is that our runtime is a lot faster than the baseline solution due to the fact that we're using multi-thread. But the trade-off is that our latency is also a bit worse. I'll discuss this further in the discussion section. But our timeliness is also a bit longer because we are waiting for out of order events, and the baseline doesn't actually just drops all, and there's a trade-off with the accuracy here. Of course, I think we can optimize this even further, and I'll talk about this in a discussion. So the first discussion note is the trade-off between runtime and latency. Because our system or our solution uses a multi-threaded system, the runtime is much less because we are able to utilize the hardware capability to its maximum potential. There's a higher efficiency there compared to the baseline solution. The problem is that there's also latency gain from the task waiting for other tasks to complete due to the fact that it's a multi-threaded system. And a second discussion point is between the timeliness and accuracy, which is how do we handle out of order events? Because there is a discussion that we shouldn't be just drop all the out of order events. There has to be a certain algorithm that's able to capture this. And of course, the timeliness will increase slightly, but if we're able to find a faster algorithm to compute this, we're able to actually just get a higher accuracy without actually sacrificing too much timeliness. A final discussion point is between the parallel DB scan and the reusable clustering. These are like alternatives towards the DB scan. So the parallel DB scan is one that actually implements a less stateful clustering algorithm, but it does waste a lot of resource because it does a lot of repetition. And because of this increases the cost when of computation. It's notable that actually it's not that useful because it would need a mechanism to indicate whether clustering is not necessary or whether it should be, and that's why I'm not really so sure about the parallel DB scan. On the other hand, reusable clustering actually is a much faster and more efficient than parallel DB scan. However, the one disadvantage that it makes the clustering node very stateful. I think parallel DB scan can be more useful if you have more resource. But moving on, these are the reference that we have. I think the most important reference is the first one, the paper by Barstim, Karim, and Young Bin, which talks about a sequential clustering-based event detection for NILM. And the reason why this is important is this is actually like our motivation behind our own solution. A lot of the NILM algorithm was explained in this paper, and a lot of the methodology and a low-level process was adapted from their paper. So if you want to learn more about our paper, it's better to look at their paper first to understand a bit about what they're doing. And yeah, the rest are just like the documentation for Flink and DB scan. Uh, Thank you for listening.